The Purdue University College of Agriculture has a long history of impact in research, education, and cooperative extension to improve agriculture and the role of agriculture in our society. One of the ways that we continue to do that is in this realm of digital agriculture. It's the fusing of our physical and social worlds to make improved data-driven decisions and actions. So you'll see a website up there in the corner. We encourage you to visit that, purdue.ag/digag. I'm Dennis Buckmaster, a professor of agricultural and biological engineering, and I also serve our dean and our associate deans as a Dean's Fellow for Digital Agriculture to coordinate activities in the college, at the university, and through to external stakeholders regarding data-driven, technology-intensive agriculture. One of the projects that we have is the Wabash Heartland Innovation Network. The WHIN project is not exclusively a Purdue project. It is a partnership with WHIN, the organization, the community foundations in a 10-county region of West Central Indiana, of course Purdue, as well as Ivy Tech Community College, and many partner organizations, farms, manufacturing firms, etc. The focus of the WHIN project is to increase the role of advanced technology in agriculture and manufacturing. In this series of brief presentations, you're going to learn of how the WHIN funds are being used to advance the technology in agriculture. So whether this particular video covers the capturing, the clustering, the collecting, or the computing, you'll have to wait to see. But in each of these cases, we are moving forward the technology in agriculture through digital means.
Hi, I'm Somali Chaterji. I lead ICAN, that is the Innovatory for Cells and Neural Machines, and I will give you a snapshot of IoT and on-device computation for digital agriculture. Okay, so we will talk about light bandwidth workloads, and we will talk about heavy bandwidth workloads that are very relevant to digital agriculture. So for the first one, we have outlier or anomaly detection for measuring sensor health. And for the second one, for the heavier bandwidth workloads, we have object detection. The motivation for doing on-device computation, so on-device as opposed to offloading everything to the cloud, is one, we want to decrease the latency and pressure on network bandwidth. Two, we want to decrease cost. And three, increase security, privacy, etc. I will also show you some test deployments of a cyber physical system consisting of sensors for moisture and for temperature connected to the edge device, which is a Raspberry Pi. For the specific algorithm that we are using is anomaly detection. And then we are also using an object detection algorithm using an NVIDIA Jetson. And I will show you some sensor deployments that have been done via the WHIN project, which is the Wabash Heartland Innovation Network project. So the ingredients for smart farm, right? This is from the FarmBeats paper from NSDI 2017. FarmBeats is an IoT platform for data-driven agriculture. And this was motivated by the large number of data streams from ubiquitous and oftentimes inexpensive sensors that are deployed in the farm for things such as soil, moisture, pH, etc. Right? And then you have networking using LoRa and BLE. And then you also have the cloud platform for long-term storage and analytics. So this is at a high level what an IoT platform for digital agriculture will look like. Now, the first little algorithm snapshot that I'll give you is on anomaly detection. Anomaly detection is essentially an algorithm that detects rare events by the fact that these events differ significantly from the majority of the data, and they are effective for detecting sensor health, and in other cases it might also tell you if there is a malicious attack on the sensor because of which the sensor is malfunctioning. Examples of these data streams in the digital agriculture setting come from moisture, temperature, nitrate. They might also be microbiome soil sensors. Now we have example deployments from our lab here at this link, which is an anomaly detection for temperature and humidity sensors that are actually also deployed in the forums, just to show you how the anomaly detection works. So like I said, anomaly detection algorithms, they detect anomalies, but we want this detection to happen close to the source of the data. So this is resource efficient. But the challenges are you have these multimodal data streams coming from multiple sensors. Now, our approach is the simpler variant of an algorithm. It is called ARIMA, which is auto-regressive integrated moving average. And the more sophisticated variant of an anomaly detection algorithm would be an LSTM, which is also computationally more expensive. We see that this ARIMA model, which is represented as a function ARIMA PDQ, where P is the number of lag observations included in the regression model. And then we have D and Q. D is the differencing and Q is the time window. So we optimize these hyperparameters for the ARIMA model and we run it. And essentially what we're doing is we're checking for sensor malfunctioning, and we're also seeing if we need to update the model, right? Because there is something called model decay or concept drift that you see in the bottom right, because of which the model may need to be updated from time to time. So this is essentially what the three parameters of the ARIMA model are. We have optimized the three parameters, and then we use ARIMA for time forecasting. We see that the mean squared error is 0.124 for our model. We test using the first 30% samples and train using the first 30% samples and test using 70%, and then we tune the model online during the testing phase. Our goal is to reduce the data transfer from the sensor node to the server, and we do this essentially using time series forecasting, and we change the error tolerance in order to decrease the data that is sent from the sensor node to the server. So in this case, we see that the error tolerance is 0, and so 100% of the data is sent from the sensor node to the server. You have the true value in green here. In black, you have the predicted value using ARIMA. In blue, you have the data that is sent, and there is no data that is not sent in this case. There are no red dots here. So in here, you see that the data sent is now 63.82% when the error tolerance is increased to 0.10. So now some of the data is being sent to the server. Here we see that the data sent is decreasing further because we have increased the error tolerance to 0.20. So now the data sent has decreased from 60-something to 50-something. And finally, here we see as the error tolerance is increased to 3, the data sent has drastically reduced to 7.44%, which is essentially our goal, to have okay error tolerance so that not a lot of the data is being sent to the server. Now, here what you see is a snapshot of the data sent. On the y-axis, there is a second y-axis that gives you the mean squared error, and on the x-axis, you have the error tolerance. So we see that as the error tolerance is increasing, the mean squared error of the model is increasing, but the data sent from the sensor to the server is decreasing. So the second snapshot is a heavier bandwidth snapshot. And for this, we have object detection. Now, object detection is done in the digital agricultural setting. For example, if you have these drone imagery. So you don't want to send all the data to the cloud. So only when there is some exceptional event that is detected, then you communicate this to the gateway node. Because object detection is a resource-intensive machine learning task. And what we use here is a convolutional neural network, specifically a convolutional neural network that is good in terms of architecture, meaning it has lesser number of parameters than a regular CNN or convolutional neural network, and the variant is a faster RCNN. You can see a preview of more details of the algorithm. We call it ApproxNet at this link. But essentially what happens is, because we are using an approximate version of the convolutional neural net, we are exiting early. So we're not going all the way through the neural network. We do early exit for approximation. And the reason we do this is because bandwidth to the cloud is expensive. Processing on the cloud could also be expensive, so you want to use the edge servers that are there at the farm, and a centralized solution can oftentimes not scale up as you have these ubiquitous data streams. So most of the video analytics queries, they involve inferencing over continents, and this is a very compute-intensive task. And these are generally too slow on edge devices to keep up with the live video stream rate, which is 30 frames per second, or they're very memory heavy. And that's how you need approximate versions of these solutions. So this is what our sensor node looks like. That HDC 2010 is our sensor. So this is an example of this embedded board with a temperature and a humidity sensor. And then you also saw the LoRa connection, the antenna at the top of the board. And these are embedded devices that we have used. For the first one is the one that is used for anomaly detection. It's a Raspberry Pi node. It does not have a GPU and it's much less expensive, whereas an NVIDIA Jetson TX2 is more expensive and it has a GPU backend. And this is what we use for object detection. Now, for object detection, we have to approximate the convolutional neural network. There are three ways of approximation that we use. We downsample the image size, and then we do early exit from the ConvNet. And the third thing that we do is we change the number of region proposals that the Foster RCNN model makes. And I encourage you to go to the link to understand a little more of the Foster RCNN structure or architecture. This is an example of the deployment at Purdue. There are 13 nodes deployed throughout Purdue, sensor, collector, and gateway nodes. And we see in general, the PDR, that is the packet delivery rate, is high. There are some lossy nodes, but in general, it's pretty good. Here we see the TPAC, which is an experimental form at Purdue, deployment of a wireless mesh network. And here we have two kinds of networking. We have the long-range LoRa and the short-range BLE communication. And finally, these are some examples of these sensor nodes. You have a temperature and humidity sensor node, and here how the sensor is connected through a wire to the embedded board, which is outside the soil. Thank you.
Thanks, Somali, so much for that overview and some instructional images and conversation about IoT for ag. I was curious when you talked about the ARIMA, the autoregressive integrated moving average. What was the temperature in those plots that you were showing?
So for our plots, we actually have a test demo. So if you go to the video link that is there on one of the slides, actually slide 4, you will see that we kind of wanted to give our audience an idea of how it works. So in our specific video link, and I also have a snapshot on slide 4, what we did is we have the temperature inside the room. So this was a test video. So we had the sensor, which has both temperature and humidity inside the room. So the temperature is around 72 degrees Fahrenheit. And then for anomaly detection, what we did is we stepped outside. I think it was in the 50s outside. So we got an anomaly score when we stepped outside. Okay. And then again, we put the sensor near the heater inside. So that was like a higher temperature. So just to give an example that if there is a sensor going awry on the field, so we actually have these same sensors in the fields, then the drastic changes in temperatures would make the anomaly score go up, showing that there is something wrong with the sensors being deployed or the specific sensor that is giving the anomaly. Okay,
I think most agricultural people, so to the engineer, it's maybe the sensor going crazy, but usually to us agriculturalists, it would be the sensor is right and the phenomena has gone weird, like the cow now has a temperature. If we're following her location, it's not that the GPS sensor is incorrect, it's that she's actually outside the fence or that sort of thing. Yeah, good.
Yeah, that's a good point. So I remember having a chat with you earlier. So in the machine learning lingo, in the machine learning parlance, anomaly detection is kind of the technical term used for this. But if you want to kind of make sure we're not giving, farmers a different kind of a view by using the word anomaly, maybe another word would be outlier detection. But in machine learning parlance, anomaly detection is the slightly more formal word. And again, for something that is like the cow stepping outside the fence. So if we were measuring like some kind of GPS coordinates or whatever, since this is a time series modeling, it is going to learn over time that something that the cow did is out of whack. So it's going to depend on what is the regular phenomenon and how is the phenomenon changing, which is resulting in a higher anomaly score, if that makes sense.
Yep. Oh, yeah. And is it possible to do in, I guess it would be autoregressive integrated moving average like, but it wouldn't be exactly that, to try to match the data that you're measuring to what was expected, not from machine learning, but from a biophysical or a logistic model. So maybe as an example, there's a certain path that we would expect an autonomous vehicle to take, back and forth, you know, turning on the ends and that sort of thing. And so you could, if something got out of whack with regard to that, that wouldn't necessarily be machine learning. It's just that you're not on the path that we prescribed, that sort of thing.
Yeah, so this REMA that we do is actually a detector of anomalies, but you make a good point. So we do this typically in scenarios like this, where you have IoT or digital ag or any of these kinds of scenarios. We do this for two reasons. So one is if the sensor is malfunctioning, and the second thing that I did not mention explicitly at the beginning is if you're modeling a physical phenomenon, like you said, right? And what happens is sometimes the phenomenon, for whatever reason, say if you have a tractor and there is a new machine or the tractor is following a new path, you might need to actually update the model because the physical phenomenon that is underlying this has changed. And this is something that is called model decay or concept drift. And what will happen is when you're doing REMA, you will see that you're getting a high anomaly score, and that is not necessarily because some sensor is malfunctioning, but the actual physical phenomenon has updated. And this is a commonly used thing in machine learning and data science in general, that for streaming data, there is a concept drift, and because of this concept drift detection, there will be an anomaly score, and this will just tell you, hey, you actually need to update your model, and then the model will be updated with the new parameters that are learned by the model. Does that answer your question?
Oh, yeah, thanks.
Okay.
And then just a question about the video, the use of video in ag. You mentioned, you know, some opportunities with the robotic arm in horticulture or the analytics on livestock movement, that sort of thing. Do you have any specific next steps that you plan to work in, taking your expertise and tools toward video analytics and ag? Like, what's the thing that you're going to work on next?
Yeah, so one of the things I was thinking along the lines of the snapshots that I have in our video that I presented. So what might happen is, so if you have something like a moving tractor that is there on the field, and as we know, the networking on these agricultural fields, that's very sparse. So you might want to use some of these opportunistic tractors or whatever that will help you carry the data load. So if you are there in a specific spot and if you see that a tractor is arriving, for example, then your object detection algorithm can tell you that, hey, you have a data ferry. So let's, transfer the data using the data ferry. So I'm kind of thinking along the lines of the areas that I work in, where you will have IoT and you will be facilitating networking using some of these object detection algorithms. So automatically when you have some data ferry that is coming close to the place where the data is, the source of the data, you trigger the object detection algorithm, and that will result in the data being unloaded into the data ferry and being carried to wherever the farmer wants to carry the data.
Yep.
So it's automatic.
Yep, sounds great. Yeah, we've been talking about lots of times, instead of just transferring the corn or the beans or the seed or the fertilizer, at the same time that we're transferring product, we need to be transferring data. So, yep, that's a good idea. Well, thanks again for sharing the information, and we look forward to future progress. Thanks.
Thank you, Dennis. This was great.